In this video, we present to you FISB, which stands for Feature-Based Image Stitching Benchmark, as part of our course project for the Computer Vision course.
My name is Abhishek Rajura.
And I am Abu Shahid. So let us begin. Image stitching finds use in various domains such as document mosaicing, image stabilization, high-resolution photo mosaics in digital maps, and satellite imagery. One of the major limitations of current image stitching algorithms is their inability to handle images taken from different perspectives with different illumination or when images are rotated. For evaluation, we use Google Landmark Images as image stitching dataset. A scene image is taken and cropped to give several sub-images. These sub-images are going to be taken as if from same perspective. To test and better evaluate our implementation, we make our own dataset of 49 natural and digital scenes. Some scenes are with huge amounts of distinct features, some with repetitive features, and some with very sparse features. They are taken from different viewpoints and perspectives with different devices and different illumination. In total, there are 261 images across 49 scenes that need to be stitched. Now, let us look at our pipeline. We feed it with input images which are then fed into the feature detector. After detection, a feature matcher is used to find corresponding features. Before stitching, we warp perspective using homography, and finally, images are blended to give the final result. First step, we find features in the images to be stitched. We use different algorithms for this, such as Sift, Arcase, Brisk, and Orb. Detailed analysis of their usage can be found in the report. After finding features across images to find corresponding feature matcher, we use various feature matchers such as brute force matcher, K-9 matcher, and FLAN. Their utility depends upon the use case. In our case, since computation and real-time results were not a constraint and dataset was rather small, brute force matcher gave us the best result. For analysis of the other two matchers, please refer to the report added in the description. Before stitching, we have to make sure that all the images are from the same viewpoint. To do this, homography matrix is calculated to bring about the needed change. Finally, let us look at image blending. 4 different techniques were applied. Alpha blending is the process that takes transparency of each pixel into account. Gaussian blending, on the other hand, is a process of blending images or objects using a Gaussian distribution. Seamless blending ensures that the color of the inserted image is likewise altered so that inserted object appears to be a natural part of the target image's surroundings. Finally, in multi-band blending, the photos that will be blended are first divided into a collection of component images with bandpass filters.
Now let us look at the studies and analysis conducted over the period of this project. Results can be depicted quantitatively and qualitatively. We have reported the quantitative results in the report using popular image quality metrics such as MSC, PSNR, SSIM, and NMI. Now we will proceed with the qualitative results. We will look at the results of this technique applied over a vast perspective of images. For the first image we used, it can be observed that alpha blending is not a seamless way to blend images since it's limited to linear transformation and thus is very restrictive in its nature. On the other hand, for the second image, we used Gaussian blending, and we can see that the resulting image is noisy because Gaussian filter is applied to each pixel, which smooths out the sharp edges and creates a softer transition between the images. Therefore, it is not a standard image blending technique for a use case. Now we see that for the scene 18, the image is produced using ORB and FLAN, and it is not accurate since it ignores the essential match point features, leading only a few images to combine. But the blender used here is multi-blend blender, which is quite sophisticated for a purpose, as we can see. Finally, we produced a panorama using OpenCV library for scene 2, and it is able to stitch most of the feature points in the image. And after rigorous permutations and combination, we observed that we got the best results for Sift with BF matcher and seamless blending. The second image is also pretty good considering FLAN is quite faster than BF matcher, but it is highly subjective to the dataset and image properties. We will use Sift plus BF matcher and seamless blending for our default FISB pipeline. Now let us look at the demo code.
We are going to look at automain.py for demonstration purposes. In automain.py, we pass the images that needs to be stitched as parameters. Here, first, we create the global map using the first image, and the remaining images are stitched iteratively by wrapping the global map. Here, for our demonstration, we are using alpha blend, but we can use any of the blending techniques that we've implemented. In our code, we have implemented alpha blending, Gaussian blending, seamless cloning, and multi-band blending. So now that when we have selected all our parameters, we are going to move to the terminal. Here, we are in automain.py. These numbers are the parameters for our pipeline, where this one represents our feature detector, that is Sift. This one represents brute force matcher. Thus 4 here represents the number of images that needs to be stitched, and this 10 here is the value of alpha. And this represents the directory path to the image that needs to be stitched. So now we can see that the process of stitching is happening and the stitching is finished, and these are the statistics. Now let's look at the stitched image in the output. So alpha blending gave us this result. Now we have already stored the results from other blending techniques, and this is what they look like. For example, this is the result from Gaussian blending. This is the result from multi-band blending. And this is the result from seamless blending. For comparison purposes, we have also stored the images stitched by OpenCV. So this is the result given by OpenCV for scene 8 and for scene 9. So for conclusion, OpenCV uses various multi-class library functions, thus making it a little slow for mathematical computation of matrices. Our FISB pipeline is pretty comparable to OpenCV in terms of quality, but since it does not consist of overwhelming number of multi-class library functions, therefore it is quite faster in building and execution time. Thank you.